Hello everybody, welcome back to another discussion dynamics. Today we'll start a new topic, namely we will start kinetics of rigid bodies. And plan for today is following: brief lecture review and then 3 examples. Without further ado, let's begin. So what I want to say what I want to say when it comes to brief lecture review. So please assume that we have a rigid body and this thing appears for the first time, yes? Center of mass, yes? Please recall that when we're talking about kinematics here, have we ever mentioned mass of the body? Yeah? Or moment of inertia? No, we just cared about geometry so far, yes? Today we will for the first time talk about mass. So this body has mass, and it has also moment of inertia, IC, about point C. Okay, so let's assume that we have net force acting on our body, let's say here, and also that there is like some moment rotating our body. So it will result in inertia, yes, plus some rotation of the body. And when you would like to put it in the mathematical form, please go for equations of motion. So force, sum of forces, will equal to m times AC. So inertia of point C. And then if we take sum of moments about point C again, then we can write this expression. Sum of moments about point C equals to IC times angular acceleration of the body. And the most important thing is marked here with red. Yeah, these equations are valid for point C only. Okay, no other point. Okay, so that's that when it comes to brief lecture review. For details, watch the lecture. Any questions? I don't hear any questions. So example number 1. As usual, please familiarize yourself with the problem statement before we start our solution. Yeah, but of course you did it before coming here, yes? My request, I asked you at the beginning of the semester is still valid. Yeah, please familiarize yourself with the problem statements before coming to these discussions, yes? There is no sense for spending our time on reading this here. Okay, so what do we have in here? We have a uniform cylinder rod, yes? And they told us that it has mass M, length L, cross section A, that is constant, and density that is also constant, density rho. And they ask us to find moment of inertia about, so IZ, yeah, which is obviously about this axis. And we're gonna do it. And then they asked us to find radius of gyration. Okay. So we're gonna just use definition, yes? So definition for IZ is here. And definition for moment of gyration is here. We just now follow definition. Okay. So this is our solution. So I believe that our dm, or maybe, you know what, guys? Maybe let me tell you what these things stand for. What is dm and what is r? So dm is here. dm is basically, or here, yeah. This is our dm. This is infinitesimal mass. Infinitesimal mass. And r is obviously distance from z to that infinitesimal mass, and dr is of course the length of dm. You should not be surprised by that, I hope. Okay, so I think that our dm can be expressed in the following way. dm is rho times d volume, yes, where dv is infinitesimal volume, yes? So we can write r squared rho dv over volume. Yes, then our dv is a times dr, right? A is constant and rho is constant, yeah? So we can also plug it here. So it would be rho a r squared dr, and that would be above along length, yes? Okay. So this is constant, right? They told us, if you look at the top right corner, you can see that a times rho is constant. So we can put it here in front of our integral, yes? Okay, so we'll end up with such integral. Oh, sorry. Rho a integral of r squared dr. Okay, guys, based on the picture, what are the integration bounds? What shall I put here and here? Yeah, from minus L over 2 to L over 2. Exactly. And I think we know how to solve that integral. I think I remember even how to solve it. So this will be rho a 1/3 r cubed from minus L half to L half. And this is equal to rho a 1/3 of L half cubed minus L half cubed. So this will be 1/12 rho a L cubed, right? And now let's go backwards, yeah? So we can also write that volume of the entire beam is A times L. So we will end up here with 1/12 rho volume L squared. And then also mass of the beam is density times volume. So that would be, 1/12 of course, 1/12 ml squared. Bang, that's the end of part A. So Iz is equal to 1/12 ml squared. You probably run into this expression in statics or maybe even in high school. So just in case you're wondering where this expression comes from, this is where it comes from. Any questions? Easy? Yeah. So now radius of gyration. So our Iz is also equal to mkz squared. So we can just equate these two expressions. So we can write 1/12 ml squared is equal to mkz squared. M cancels out. And triumphantly, we can write that our kz is equal to square root of 12 divided by 12 L. Okay, so this is answered part A. Answer part A, or part 1, and this is part 2. Questions? Okay, so what? Example number 2? Yes? Okay. As usually, please familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? Aha, we have a cabinet here. Somebody is pushing the cabinet, so we can model that person with force P, basically here, yeah. So we know the weight of the cabinet, we know how strong is that push, yeah. We know the coefficient of friction between cabinet and and the ground. We know that we are in kinetic friction regime, right? And we know the geometry. As usual, we know the geometry. And if we don't know it, we can always measure it, yeah? And they ask us to find H, so the highest point of application of that force P, so that our cabinet does not tip over. And they also ask us to find corresponding acceleration of point C. Yeah. So usually in this course they call it point G, you know, the center of mass. I call it point C. Okay. So just I don't know, get used to it. I don't know. Okay. So do you remember our recipe from the first part of the semester for kinetics? So we just follow it here. We'll start with our free body diagram and kinetic diagram. So in here, I just would like to model this cabinet as a rectangle, where center of mass is here, C. I'm just gonna copy paste it to my kinetic diagram, okay? So now the question is, what forces act on our system? So we have obviously mg here, mg. I think that there is also, that guy is pushing that thing, yeah? So there's force F, force P, yeah, and this is H. And this is D. Okay, are there any other forces acting on our system? Anybody? Friction, yes. And there's one more? Normal, yeah. So listen, Hamilton, where would you apply them? Sure. That's closer to what I want to squeeze from you. So would you apply it at this point, or at this point? Please notice that we no longer are in particles dynamics. It's not one, yeah, this is a rigid body, yeah. So it's made of particles. Yeah? So you want to apply that friction force here, maybe here, or maybe here. Where? The one on the right. Okay, and why? Beautiful. Yes, exactly. So this is the point of contact right before it starts tipping over. Exactly. Yes. So this is point of contact right before it starts tipping over. Oh, sorry, typo. Oh, okay, so we have TF in here, as you said, friction, and also normal force. And I believe there are no other forces acting on our system, just these four, yeah? And on KD, we're just gonna follow our routine. So in here, we'll put MACX, MACY, and also we will put here IC alpha body. Okay. What you guys can tell me about AC? What's the value of AC? It's 0. Yeah, because it is not tipping over. Yes, it is not rotating. And if it's not rotating, what shall I set this value to? Also 0. Yeah, because this is the trajectory of our AC. Trajectory of point C. Great. Okay, so we are done with FBD, we are done with KD. Second step, of course, you remember, equations of motion. So let's do sum of forces in the x direction. So in here we only have P minus TF, and this will be equal to MACX, exactly. Okay, in the y direction, there is also something happening. Yes, we have minus mg plus n, and this is equal to mcy, yeah? But you guys told me that this is 0. So this is 0. And we found normal force acting on that corner. So n is equal to mg. Great. And this is a new equation. We have never seen it in the discussions. You've seen it in lectures. So moment about point C. How many forces rotate about C? I think 3 forces, yeah? P, TF, and N. Okay, so P rotates in a positive or negative fashion? Negative fashion, yes? So minus P, H minus D, right? Now TF rotates in the negative direction as well. So we have minus TF, D. And N rotates in a positive direction. So it will be, and by the way, what was this distance? I think this is W. Let me scroll up the board. Yep, this is W. So in here we'll have plus N W divided by 2. And this is equal to IC alpha body. But again, you guys told me that this is 0. Okay, so what was the next step in our recipe? We will just count equations and we'll count unknowns. Okay, so we have this equation here. We have this equation here. This is equal to 0. Okay, so I think that ACX is not known. And I think that the distance is not known, yes? Oh, and TF also. But we can fix that problem, yes? Because you guys told me, no, you didn't tell me. They told us that we have in kinetic friction, we are in kinetic friction. So we have kinetic friction. So TF is equal to mu k n, and we just found n. So TF is equal to mu k mg. Okay, so I'm just gonna plug this one here, okay? Instead of TF, I'm just going to put here mu k mg. Okay, and we ended up with 2 equations and 2 unknowns, right? Okay, so if you solve it, you will end up with, we can actually plug in values. So ACX will be 1 over m P minus mu k mg d. So plug in values. ACX is equal to 1 over how much? 230 divided, yes. So I just do it, just to remind you that this is 230 divided by 32.2. Yes, we are in US units. That was 70, if I remember correctly. That was 0.28. This is 230. And D, I forgot how long was that? 2. Yeah, I made a mistake. There was somebody. Of course not, because I made a mistake. Yes, sorry. So this is, I'm gonna remove it. Yeah, thank you, Anna. Or Anna, actually, you're Anna, yes? No, or Anna, or both? No, you must decide. Okay, grab your calculators and obtain that this is approximately 0.784 feet per second square. Okay, and this is positive value, so our AC will have this direction, 0.78400 feet per second squared. Okay, and now if you want to find h from the other expression, just find it, grab your calculator, and obtain that h is approximately 2.21357 feet. Okay, so this is the height that guy can push the cabinet before it starts tipping over. If he pushes it a little bit higher, it will start tipping over. Alrighty, questions? How do you like it so far? Is it okay? Yeah? So we just follow the same recipe. So maybe this is a good moment to say that sentence I want to say. So actually, kinematics of rigid bodies does not much differ from kinematics of particles, yes? Do you see that? Yeah. So in here, our body has some volume, yes? Our bodies here are larger than particles, yes? Yeah. However, we can boil down the analysis of the motion to this point. Yeah, so we can actually consider this body as a particle. Yeah. And the particle that has mass, and also it has something like IC. Do you see that, guys? This is a little bit abstract, yeah? In other words, the shape of the body does not matter here. So the solution, would the solution be different if this cabinet has different shape, but same location of center of mass, same mass, and same IC? No. Yeah. Okay, think about it, and maybe before you think about it, we can do example number 3. All right, example number 3. Please read and understand the problem statement before we start our solution. Okay, so what do we have in here? We have, now our beam lays on the, I don't know, table or ground. So this is top view, okay? This is top view. And gravity acts into the page. Yep. However, there is no friction between beam and table. So actually, we can ignore all the motion that is perpendicular to the board. Yeah. Okay. So what do we know about the beam? We know that it has mass m. We know its length, m and l respectively. We also know that moment of inertia about c is 112 ml squared. Oh, by the way, this is exactly what we derived like 20 minutes ago. And we also know that there is a force P acting on that body. Yeah. And we know that this is important. We know that our system starts from rest. So once you see that in the problem statement, you can easily set up every single velocity to 0. Velocity of every single point is 0. And what do they ask us to find? They ask us to find h again, yes? Yes. So they ask us to find point of application of point of force P, such that this guy is 0. So this is our requirement. Find h such that AB is 0 vector. And also once we know that this is 0, we should also find acceleration of this point, of point A. Questions about the problem statement? If not, we will just follow our recipe. Okay, so I will surprisingly start with FBD and KD. So let me draw the beam. This is our center of mass. And I'm going to copy that beam to my KD. Okay, so what forces act on our system? mg. Yeah. mg acts on our system. And now we have to have reaction force acting back. Yes? So there is like more than one point of contact between the beam and the table. So let's just write here that the normal force distribution balances out mg. Okay? Normal force distribution. That obviously it acts out of the page, yes? Normal force distribution balances out mg. Yeah, if you want to write it quicker, just write no motion in direction perpendicular to the page. Yes, there's no motion in the direction perpendicular to the page. Okay, and is there any other force acting in our system? Ah, this one. H, and this is L. Okay. That's all, yeah, that's all. So now we can write MACX, MACY, and also IC alpha body. Great. Next step, equations of motion. Unless you have questions, guys. Oh, yeah. No. This is the. Okay. There's no friction. There's no friction. Okay. Thank you. Yeah. And that's why I don't know what to write here basically because it's like a lot of these little forces supporting the beam. So it's like a force distribution. Yeah. But we don't care about that because we care only about motion in this direction. Yes, we don't care about motion in this direction. No worries. Thank you for the question. Yeah. Good. That was individual teaching for a second, but sorry guys. Okay. I'm not a teacher. I'm like a grotesque teacher. Yeah. So forgive me that. Okay, Ion. So we're gonna follow our routine. Sum of forces in the x direction. Sum of forces in the y direction. And sum of moments about point C. No other point. Okay. So far. Right now, only point C, okay? So what do we have along the x direction? Only one force, okay. So we have P. And this is equal to MACX. Okay, along the y direction, 0. And this is equal to MACY. Okay, great. So that means that our ACY is 0. And now, how about moments? So P rotates in a negative fashion, yes? Yes. So it will be minus P H equal to IC alpha body. Okay, we're done with our equations of motion. So let's see how many equations do we have? For sure 2. And how many unknowns? This is not known. This is for sure not known. And I think we also don't know the point of application, yes? Dang. So we have 2 equations and 2 unknowns. 3 unknowns. And I think I need some help how to find the third equation. Do you remember what was the recipe like a couple of weeks ago? You have something on your face. I don't hear you. So you must say it louder. I'm sorry. Sorry. Yes, exactly. Perfect. So we're gonna do acceleration analysis. Yes. Awesome. Anna or Anna. Thank you. Sorry. Yeah, we need third equation. We're gonna do acceleration analysis. Yes. So you said from B to C? Yeah, exactly. From B relatively to, no, let's do from C, sorry, C with respect to B. Great. So AC is equal to AB plus alpha body times RCB minus omega body squared RCB. By the way, problem, the system starts from rest. Yes, so check this out. We can set up this to 0. 0. System starts from rest. Okay, so this is ACX, ACY 0. Yeah, but I think that ACY was 0. Yeah, so let's set this to 0. We found it earlier. So this is 0. They told us that this is 0. Yeah, 0, 0, 0 plus 0, 0 alpha body times this vector. Okay, let me draw it in the picture. So this is the vector. Maybe green one. My favorite color, by the way. So this is R CB. And this is obviously equal to 0, L half 0. Green is a color of hope, just as a digression. Okay, if you do that determinant, you will end up with following expression. It will be minus alpha body L half 0, 0. So that means that our, so I can just copy this one here, yes? Great, and from the X component, we have that ACX is equal to minus alpha body L half. Okay, so thanks to Anna, we have our third equation, yes? So we can copy these guys. We can copy this guy here. And all of a sudden, we have 3 equations and 3 unknowns. And I have no doubts, guys, that you know how to do it. So these are 3 equations and 3 unknowns. And this will be black. Oh no. Okay. So if you solve that, you can end up with ACX, H, and alpha body equal to, respectively, P over M, L over 6, and alpha body equal to minus 2P ML. Yeah, it makes sense. Alpha body rotates clockwise, yeah? We should obtain a negative value, yeah? So our AC is basically equal to P over M 0, 0. And our alpha body, vector-wise, is equal to 0, 0 minus 2P divided by ML. Yeah, this is clockwise. Okay. So these are actually side products, yes? These are side products of our solution. Side products of our solution. Because what they actually ask us for is this guy, yeah? What is the point of application? This is answer part A. Part A. I think this is a good time for questions. Yeah. Yeah. Am I doing a good job so far? Yeah. Everything is clear? Yeah. We're on the same page. Cool. Thank you, guys. Okay, so let's do part B and let's go home, yes? Or wherever you want to go. So what was the part B of that problem? Aha, find acceleration of this point, yes, after you solved part A. So I can equally ask you, Anna, to repeat your answer. Yeah. That was a rhetorical question, but thank you. Okay, part B. This is part B, yeah, part B. So it's acceleration analysis between A and, I don't know, do you want between A and B or A and C? Doesn't really matter. A and B, let's say. So AA is equal to AB plus alpha body times RAB minus omega body squared RAB. Story is exactly the same. So this is 0 because system starts from rest. This is 0 vector because they told us. And AA is equal to 0, 0 minus 2pm. No, sorry, 2p divided by ml times 0, L0. Right? Because this is our vector, RAB. Let me put it on the board very quickly. So this is our RAB. You can clearly see that its components are 0, L0. Great. So if you solve that determinant, you will end up with following value: 2p divided by m, 0, 0. And this is the answer to part 2. That's it. Questions? I don't see any, so I can only wish you a nice afternoon. Thank you for today. Bye.